Okay, we are continuing our examples for comparing two population means. Let's have a look at this example. 10 randomly selected students scored the following marks in the final exam in economics and statistics. So we have 10 students, and for each student we have a mark for economics and a mark for statistics. For example, for student 1, scored 75% in economics and 71% in statistics. Can you conclude at the 5% level of significance that the mean mark scored in the final exam in statistics is lower than the mean mark scored in the final exam in economics? Okay, so if we compare two population means, we first need to determine whether we are working with dependent or independent samples. Now, in this case, we have 2 marks for each student. So there is an association between each observation in the first sample, the economics sample, and each observation in the second, the statistics sample. So we are in fact here working with 10 paired observations, and therefore we say that we are working with dependent samples. Now, how do we treat dependent samples? First of all, we define a new variable d, which is the difference between the two observations from sample 1 and sample 2. Okay, and then in this table, we look at the assumptions and the test statistics. So the assumptions, if we are working with dependent samples and ND is large. Now, ND is the number of pairs or the number of differences that we are working with. So in our example, we have 10 students, so we will have 10 pairs or 10 differences. If the sample size for the differences is large, then this will be our test statistic. Now, the test statistic is the mean for the differences. So that is why we use the subscript D. It indicates that we are working now not with the individual samples, but with the differences between the two samples. So the test statistic is the mean of the differences divided by SD, which is the standard deviation of the differences over the square root of the number of differences, the sample size. Now, if we are working with a large number of differences or pairs, then this test statistic follows an approximate normal distribution. And if you look here at the second row here, if we are working with a small number of differences or a small number of pairs, then we have to assume that the differences come from a normal distribution. And then my test statistic, the formula looks exactly the same as the previous one, but now the distribution is the t-distribution. For the rejection region, you will see if we are working with a large number of differences, because the test statistic follows the approximate normal distribution, we will use the Z tables to get our critical values, whereas if we are working with a small number of differences or pairs, my test statistic follows the t distribution, and therefore our critical values will come from the t distribution. Okay, so back to our example. The first step in a hypothesis test then is, of course, to state the null and the alternative hypothesis. Now, if you look here, the last sentence, can you conclude at the 5% level of significance that the mean mark scored in the final exam in statistics is lower than the mean mark scored in the final exam in economics? So we know that we are working with a one-sided alternative. We can write down our null hypothesis that the mean mark scored in statistics is equal to the mean mark scored in economics, versus the alternative that the mean scored in statistic is less than the mean scored in economics. Now we can rewrite these hypotheses in the following way. The null hypothesis can be rewritten as mu s minus mu e is equal to 0. And the alternative is that the difference between these two means is less than 0. Okay, and we are going to use this when we calculate our test statistic. So let's just go to Excel. You can go to the raw data in the Excel spreadsheet and we will calculate these differences. Okay, so what we have here is we have the 10 students, and for each student we have the economics and statistic marks. So to calculate the differences from the previous slide, our differences was the difference between statistics and economics. So we will calculate the difference as the statistics mark minus the economics mark. So that is the difference for the first student, and we do that for all 10 students. So now we work only with the differences. We ignore the rest of this information and we work only with the differences. And for our test statistic, we need the mean and the standard deviation of the differences. So I will now calculate the mean or the average of the differences. And that's equal to minus 1.3. And I will also work with the standard deviation, and we work with the standard deviation dot S for the sample standard deviation. The standard deviation of the sample standard deviation of the differences, which is 3.83. And we will now use this in our formula for the test statistic. Okay, of course, our level of significance is 5%, and now we can substitute the mean and the standard deviation of the differences calculated in Excel into our test statistic formula. So the mean of the differences is minus 1.3, and the standard deviation of the differences is 3.83, and we divide it by the square root of the number of pairs or the number of differences. Because we have 10 students, my n is equal to 10, and I get a calculated test statistic of minus 1.07. Now, because we are working here with a small sample, only 10 pairs, our test statistic follow a t-distribution, and therefore our critical value for the rejection region will come from the t-distribution. So if this is my t-distribution, my critical value will be the t-value, so that the area to its left is equal to 0.05. Okay. If you work, depending on what tables you are working with, but if you are working with the tables that only give the positive t-values, then you will find t 0.95, which is the right critical value, and then to get the left one, you will just take the negative of t 0.95. Okay, so negative t 0.95 with 9 degrees of freedom. Remember, my degrees of freedom is n minus 1, so we have 10 pairs. So 10 minus 1 is 9, and my critical value is minus 1.833. Now my calculated test statistic value is minus 1.07, and that is greater than minus 1.833. So it does not fall in the rejection region, and we do not reject the null hypothesis. So if this is my t-distribution, my rejection region is everything to the left of negative 1.833. So my rejection region is over there. My observed test statistic value was minus 1.07. It lies to the right of minus 1.8, so it falls in the acceptance region, and therefore we do not reject the null hypothesis. You can also find the p-value. We did several of these examples previously, and we can also now do it in Excel just after this. But your p-value is then 0.156, and because that is more than our level of significance, which is 5%, we do not reject the null hypothesis. And then finally, we come to our conclusion. We say that there is not enough evidence at the 5% level of significance to conclude that students scored less in the final exam in statistics than in the final exam in economics. So we can now in Excel also find our critical value and our p-value. So to get our critical value, we make use of the T inverse function. We want to find 0.95 and our degrees of freedom is 9. So our critical value on the right is 1.833. So our critical value on the left is just minus 1.833. You could, of course, also, to get that directly, not use the probability 0.95, but the probability to the left as 0.05. And then you will just get the negative 1.833. So that's your critical value for the rejection region method. So let's just put that in as your critical value. And then for your p-value, we use the function t.dist. Our x value is minus 1.07. That was our calculated test statistic value. The second argument is the degrees of freedom, and that is a 9. And then we want to get the cumulative distribution function and not the probability density function. So we put in true, and we get 0.156 for our p-value. And that is the same that we have here on our slide. And as we said, we conclude, therefore, that there's not enough evidence to conclude that students scored less in the final exam in statistics than in the final exam in economics.